All right, so get this today's deep dive. Calculus.
Oh, yeah, fun.
Yeah, you and me both, right?
Yeah.
But you handed me this lecture on something called parametric equations.
Yeah.
And, I got to say, I was a little unsure how exciting this was going to be, but
Right.
honestly, every time we do these deep dives, it turns out to be fascinating. There's always something kind of cool hidden just below the surface.
Yeah, definitely. I think what's really interesting here is how they try to explain all this with an example of an ant crawling on a curve.
An ant, okay,
Yeah.
like seriously, when was the last time any of us actually sat down and thought about an ant's movements mathematically?
Well, I think we can all kind of picture it, right? Like an ant moving around, its pack all kind of curvy and stuff.
Yeah.
If you were to actually plot that out on a graph, you'd see how its position changes over time.
Oh, okay. So it's not even just about where the ant is at one moment, but
Yeah.
it's more about like its whole journey, how its position is always changing.
That's it. That's it. And that's where this idea of slope comes in, which, you might remember slope of a line tells you how steep it is. And in this case, we're interested in the slope of the ant's path at different points.
So like a really steep slope would mean the ant's on some kind of intense climb, and then a flatter slope is more of a leisurely stroll.
Exactly. But here's where it gets kind of tricky, and this is what the lecture really dives into. We don't have some simple equation that just tells us the ant's y position based on its x position.
Yeah.
Instead, we've got these separate equations, and they both involve time. They're telling us how x and u are changing over time.
It's like instead of a direct flight from point A to point B, we're taking this detour through time zone t. So how do we even figure out the slope of the ant's path when we don't have that direct link between x and y?
See, that's the really clever part. So instead of trying to find the slope directly, which would be like trying to do dx, that's how
Yeah.
I'd usually do it. What we do is find how u changes with time, so that's dt, and then how x changes with time, that's d dt. So it's almost like we're breaking the ant's movement down into smaller pieces?
Okay, so we're looking at its vertical movement and its horizontal movement separately, both with respect to time. I'm with you so far. But then, how do we get to the slope we want?
So this is where that aha moment comes in. You can actually just divide the rate of change of y with time by the rate of change of x with time, and boom, you've got the slope of the ant's path.
Wait, really? It's that simple?
No, it's that simple, yeah. It's
So,
divided by dx dt.
wow. That's incredible. It's like we've discovered this shortcut, this secret passage in the calculus maze.
Yeah, I like that. That's a great way to put it. And the cool thing is that this lets us analyze all sorts of complex curves, even if we don't have a nice, neat equation like y equals f of x.
This is already kind of blowing my mind a little, and we're still just talking about an ant here.
Yeah, yeah.
So the lecture actually walks through how to do this, right? They use this approach, these parametric equations, to actually find the slope of the ant's path at a specific point in time.
They do, yep. And they even give us a specific time when t equals 1, and they plug it into the equations, do a little calculus magic, and we find out that the slope of that ant's path at that exact moment is 0.
Okay, so slope of 0? What's that again?
So picture it this way. Imagine the ant's at the very peak of a hill on its little journey. At that exact point, the tangent line to its path would be perfectly horizontal, and that's what a slope of 0 means.
So the ant's taking a little break at the top of its anthill. I love how this math just pinpoints that moment. But something tells me this is bigger than just ants, right? I mean, you did say this applies to a lot more than that.
Oh, for sure. This and example, it's really just the tip of the iceberg, believe me. These parametric equations, they're like a whole new lens for looking at the world.
All right, you've got my attention. What else can we analyze with this math wizardry?
Well, for example, imagine trying to track something like, say, the price of Bitcoin. It's all over the place, right? Constantly fluctuating. Parametric equations can actually help us make sense of that.
Okay, you mentioned Bitcoin, and now I'm really curious. How does that work?
Well, let's talk about that after we take a quick break. Hang on.
Okay, so Bitcoin, parametric equations. Help me connect the dots here.
All right, so remember we were just talking about the ant, right? And how its position changes over time. Well, imagine if you tried to plot the price of Bitcoin on a graph.
Yeah, okay, I can see that. So time on one axis, and then, like, the price on the other.
Exactly, and that graph would be pretty wild, right?
Yeah.
All those crazy jagged lines and sudden spikes and dips and everything.
Oh, yeah, definitely. Enough to give you a headache trying to figure out what's going on.
Totally. And that's actually where our little ant buddy comes back into play. Because remember how we were using parametric equations to sort of break down the ant's movement into these smaller, more manageable pieces? Well, we can do something similar with all those Bitcoin price fluctuations.
Okay, I think I see where you're going with this. Go on.
So instead of trying to come up with some giant, scary equation that tries to explain the entire history of Bitcoin's price, which, good luck with that, right?
Right.
We can use these parametric equations to look at specific time periods or specific trends, and we can start to analyze how different factors, like maybe there's a big news event or some new regulation, or even just like online hype, how all those things might be influencing the price at a particular moment.
Oh, okay. So it's like we're kind of zooming in on these smaller chunks of that crazy Bitcoin graph and then using parametric equations to look for patterns or understand like what's driving those many trends within the larger chaos.
You got it. Exactly. And then by breaking it down like that, we might start to see some pretty interesting relationships. Like maybe we notice that every time a certain celebrity tweets about Bitcoin, the price jumps up for a little bit.
Interesting.
Or maybe we see that after some big regulatory announcement, there's almost always a dip in the market.
Wow, that's actually really cool. It's like we're using math to decode the language of the market.
Yeah, yeah. That's a really good way to put it. And the best part is this is just one example. I mean, parametric equations have all sorts of applications across so many different fields.
Right. Like, didn't you say we could even use this stuff to analyze things like the trajectory of a projectile?
Oh, absolutely. Like if you think about launching a basketball or even a rocket, we could totally use parametric equations to map that out.
See, that's what blows my mind about all of this. This is calculus,
Yeah.
and yet we're talking about something as concrete as launching a rocket into space.
It's all about those underlying principles, right? It's the power of breaking down complex motion into those fundamental components. So with a projectile, for example, we can use those parametric equations to describe its horizontal motion and its vertical motion separately. And then each of those is affected by things like gravity and air resistance.
Right, right. And then by understanding each of those pieces individually, we can predict the overall path of that projectile, like super accurately. It's like having a crystal ball. But, okay, hold on. You said there were even more applications. What else can we use these parametric equations for?
You might be surprised to learn that we can even use them to understand sound.
Wait, really? Sound? Okay, now I need to hear more about this. Sound and math, huh? Not something I would put together, but I'm ready to be amazed. How does math help us understand sound?
Well, if you really break it down, sound waves, they're just vibrations, right? Traveling through the air. But the key is they create these patterns of changing pressure.
Okay, and patterns we can usually find with math. Right.
Exactly. So imagine taking those pressure changes and actually mapping them out, like visually on a graph.
Oh, okay. So we're talking about taking something that we hear and turning it into something we can actually see.
Yeah, and once we have that visual representation of the sound wave, that's where we can bring in those parametric equations. They give us a way to describe those shapes no matter how complex they get.
Okay, I think I'm starting to get it.
hmm
But why is the shape of the sound wave so important?
Because the shape is what determines a lot of what we actually perceive about the sound, like the frequency, for example. That's what we hear as pitch.
Okay.
A higher frequency means a higher pitch, but also things like timbre.
Timbre. Right.
That's like the unique quality of a sound. It's how you can tell the difference between a guitar and a piano, even if they're playing the same note.
Oh, okay, yeah.
That's all about the shape of the wave.
So you're saying with parametric equations, we can basically break down those complex shapes
Yes.
and then actually like understand the math behind why different sounds sound different.
Exactly. And potentially even manipulate those sounds too. Like think about synthesizers.
Oh, interesting.
Or all those digital audio programs people use to make music. They're all based on these mathematical representations of sound waves. You can change the frequency, the amplitude, all that stuff.
It's like having a toolbox full of mathematical instruments to just sculpt sound however you want.
Yeah.
This is incredible.
It's pretty amazing what you can do with a little bit of math, right?
Seriously. We went from ants to Bitcoin to rocket launches, and now we're talking about musical masterpieces. Who knew calculus could be so multi-talented?
I know, right? Parametric equations are seriously powerful stuff. They have so many different applications.
So for any listeners out there who are feeling inspired right now and want to dive even deeper into these mathematical ideas, what would you suggest?
Well, if you really want to go further, you could look into something called differential geometry.
Differential geometry, got it.
Yeah, it takes a lot of the ideas we've been talking about today and kind of kicks it up a notch, Explores curves and surfaces in even more detail.
Excellent. We'll have to add that to the list for a future deep dive then for sure. Maybe even with you back as our expert guide. What do you think?
I'm always down for a good deep dive.
And listeners, thank you for joining us on this journey as well. Hopefully you're leaving today not just with a better grasp of parametric equations, but also with a sense of wonder about all the amazing connections hiding in plain sight. From the tiniest ant to the vastness of outer space, and even the music we create, it's incredible how math has a way of tying it all together. Until next time, keep those brains buzzing, and don't be afraid to explore the fascinating world all around you.